Okay, I guess I'm going to go ahead and get started. There might be a few more people that join us after we get started, but it's about 1 o'clock, so I'll go ahead and get started. So, just a couple of things before we jump into the material today. Just remember that the first test is due Monday, and that's over chapters 1, 2, 3, and 4. And I've already covered that material, so if you missed the lectures I had on those, I do have recordings that I sent out in an email. So if you need to, you can watch those as well. And just make sure you take the practice test before you actually take the the test itself. Okay, so there is a practice test in my math lab that you should look at. Okay, having said that, so last time we started talking about chapter 5. Um, Now, if you remember, chapter 5 is about discrete probability distributions. Remember, discrete means the numbers, the data that we're working with, the numbers have to jump by a certain amount, like 1, 2, 3, 4, 5, 6, 7. When we get to chapter 6, we're going to look at what's called continuous data distributions. And that's where the numbers can take on any values. They don't have to jump by a certain amount. So, 1.1, 1.2, or any number in between for that matter. And those are a different case. Okay, so we'll look at that in chapter 6. But for now, we're focused in on these discrete distributions where the numbers are jumping in our data set. And we kind of talked about in 5.1 kind of a quick overview of discrete distributions. And now we're looking at some special types of discrete distributions, okay? And the first one we're going to look at um, is the binomial distribution. I started talking about this last time, but I'm just going to start over. This is 5.2, where we focus in on this very specific kind of discrete distribution known as a binomial distribution. And then in the next section, we're going to look at another special case of a discrete distribution known as a Poisson distribution. But just know that the next two that we're going to look at are technically discrete distributions. They're just special cases that have special conditions that need to be satisfied in order for them to be classified as either being a binomial or a Poisson distribution. Okay. And if we can identify them as being binomial or Poisson, then we know how to sort of tackle uh, the problem at hand because we'll be able to find out the probability of certain things happening. We'll be able to find the mean of the distribution and the standard deviation of the distribution and whatnot. So it's important to be able to identify the kind of distribution you're working with first. Okay, so let's talk about the binomial distribution. As I said, it is a discrete distribution, but it has 4 conditions that need to be satisfied in order for it to fall into this special category of a binomial distribution. And so the 4 conditions that need to be satisfied. First, we're going to be running a certain number of trials, and they have to be fixed. When you do a binomial distribution, however many trials you're running, it must remain the same every time you run the procedure. And then every time you run a particular trial, there has to be exactly 2 outcomes possible. Exactly 2. Okay. The third thing is the probability of success has to be the same for each trial. So with respect to 2 outcomes, there's going to be exactly 2 outcomes that are possible. One of them is going to be called a success, and the other outcome is going to be called a failure. And the probability of succeeding has to remain the same every time you run a trial. So that can't change when you run different trials. The probability of success has to be the same. By the way, the probability of failure is going to be called Q. We're going to label that with a Q, and that's going to be 1 minus P. So for example, let's say the probability of succeeding is like 40%, which is 0.4 written as a decimal, and the probability of failure would be 60%, which is 1 minus 0.4, that would be 0.6. And so Q stands for the probability of failing, right? Whereas P stands for the probability of succeeding. But the probability of succeeding must remain the same every time you run a trial. That's one of the conditions here for it to be binomial. And then the last condition is the trials have to be independent of each other. So when you're running your trials, the outcome of the first trial can't affect the outcome of the second trial. They're independent of each other. They have no effect on each other in any way at all. And so as long as you have these 4 conditions, then our discrete distribution actually is a special case called a binomial distribution. And then you'll notice at the bottom here, we'll be able to calculate the mean of the binomial distribution and the standard deviation of it with these formulas. And we'll talk about these more in a second. And then at the very bottom, you can see we're able to calculate the probability of a certain number of successes out of n trials, which, by the way, is how we define a random variable in this particular situation. So the random variable in a binomial distribution, now remember, x is the way we define a random variable. So x stands for random variable. And in this case, for a binomial distribution, it's the number of successes that you have when you run your n trials. And down here at the bottom, we'll be able to determine the probability of getting a certain number of successes when we run our n trials. Okay, so that's the probability formula. So I'm going to go ahead and jump into the homework and kind of give you a sense of how this works. Okay, so I just want to make sure, can everybody see the homework on the screen? Sophia, can you see it?
Yes.
Okay. So first, I want to go over an example or two where we just kind of check the four conditions for binomial and just get familiar with that idea. And then we'll actually work out some problems where we find like the probability of x successes over a number of trials, okay? So this first one says, determine whether a given procedure results in a binomial distribution. And if it's not binomial, identify the requirements that are not being satisfied. So it says, determine whether each, so I guess what they're doing here is they're sampling 150 MP3 players and determining whether they're acceptable or defective. So maybe this is a company that makes MP3 players, and then after they make them, they go through a quality control process and they look at them and decide whether they're acceptable or defective. So we want to know whether this actually is a binomial distribution or has a binomial distribution. So we have to check the four conditions, okay? So the first one, let me go back to it. The first one was we have to have a fixed number of trials. So that would mean that when we do this procedure, we have to always have 150 MP3 players. So if I were to do this again, I would have to do it with 150 MP3 players every time in order for this to be binomial. You can't change the number of trials. And if it's going to be binomial, that has to stay the same. So as long as we keep it at 150, the number of trials at 150, then that satisfies the first condition. The second one said there has to be two possible outcomes for each trial, exactly two. So in this case, it's either acceptable or defective, right? So those are your exactly two outcomes when you run your trial. Okay, and then the next one, the probability of success has to be the same for each trial. So I'm going to make an assumption here. Whatever the manufacturing process is for the MP3 players at this company, we're going to assume that maybe, let's say, 1% of them that are made are defective. So I'm talking about the large population of this manufacturing of MP3 players. If you look at the entire population of MP3 players, we're going to assume that the manufacturing process that they have generates the same percentage of acceptable versus defective MP3 players. So let's say 1% are defective and 99% are acceptable. As long as that doesn't change, then the probability of success will remain the same. Success here, let's say, is acceptable and failure is defective. So the acceptance rate would always be 99% and the defective rate would always be 1%. Now, if the company were to improve the process of making their MP3 players and had a different manufacturing process, then maybe that percentage might change. But let's assume, they don't really tell us, but let's assume that whatever process they go through, the probability of success remains the same for each trial. So if that's the case, then the third condition would be satisfied. And then the fourth condition is the trials have to be independent of each other. So that's the idea that I make this MP3 player and it's defective, that should not affect whether the next one that's made is defective or not. It's hard to know because, I don't exactly know the process of making MP3 players, but let's assume that that's the case, that whether this MP3 player is defective or not does not affect whether the next one is defective or not. So if that's the case, if they're independent of each other, then the fourth condition would be satisfied, okay? So that's what a binomial distribution would look like, right? Would have to satisfy those four conditions. And this one is pretty close, it seems, to satisfying those four. So this probably would be a good candidate for modeling it as a binomial distribution, okay? Okay, so what would not be binomial? Um, okay, so here they say they treat 200 bald men with a special shampoo and record how they say their scalp feels after using this. So if you look at it, the fixed number of trials is 200, I guess. Um, so it satisfies the first condition. The second condition, though, is where we run into a problem, because when someone says how their scalp feels, there could be more than like one possible response, or two possible responses, rather. So uh, there's not exactly two outcomes possible here. There's more than two outcomes that are possible. And so that's where this breaks down. This would not give us a binomial distribution because of that. Another example is if you randomly select 100 citizens of a state and record their nationalities. So again, n is 100, that's fixed. So it satisfies the first condition, but the second condition, there's lots of different nationalities that people could have, so there's not exactly two outcomes, so this would not be binomial. By the way, binomial has the word bi in it, which means two, and that refers to the, having exactly two outcomes. And a lot of times that's the problem. You don't have exactly two outcomes. This one says you survey 20 married individuals and record if they have been divorced. Okay, so n is 20, so that's fixed at 20. And then when you run a trial, you either get someone who's divorced or not divorced. And so there's exactly two outcomes, right, when you run a trial. And then the third condition is that the probability every time you run a trial has to be the same. So as long as you're doing this, say, in the same country at the same moment in time, there's a certain percentage of the population that's been divorced or has not been divorced. And as long as that percentage doesn't change, then the probability, like when you randomly pick someone, the probability that they're divorced or not should be the same. So in that case, yes, the probability would be the same. Now, if you did this over a period of time, then the divorce rate might be different. And then the randomly picking someone, the probability of them being divorced or not might change depending on when you pick them. So let's assume that you're picking all these people at the same moment in time in the same country so that the probability of being divorced is the same. If that's the case, then it would satisfy that third condition. And then the trials have to be independent of each other. So I don't know if that's exactly true. Maybe this person gets divorced and they have a friend, and that maybe influences them to get a divorce. I guess that's possible. But for the most part, let's assume that everyone independently, has decided whether they're going to get divorced and they're not influenced by someone else being divorced or not. If that's the case, then it would satisfy the fourth condition. And then, of course, this would be binomial. Okay. Okay. So does anybody have any questions about that, first of all, before we move on? Okay. So essentially, binomial is a discrete distribution that has to satisfy those four additional conditions in order for it to be binomial. Okay. And the nice thing about having a binomial distribution is we can use those little formulas to find the mean and the standard deviation and the probability of X successes out of N trials. And so that's what I want to go to next. So this next problem says, assume that when adults with smartphones are randomly selected, that 64% of them use them during meetings or classes. So this is a fact about the population at large. We know that if you look at the entire population of smartphone users, that 64% of them use them during meetings or classes. Okay, so that's a fact about the population. That percentage is not going to change for this particular problem. Okay, and then what do we do? Well, they say we're going to randomly pick 8 people from the population, 8 smartphone users, and we're going to ask them whether they use their smartphone during classes or meetings. And we want to know the probability that out of those 8 people that we randomly selected from the population, we want to know the probability that exactly 5 of them say that they use them during meetings or classes. Exactly 5. Okay, well, it turns out that this is actually a binomial distribution, and for that reason, we can actually use that probability formula that I showed you to calculate this probability. So first of all, let's check real quick and go through, check the 4 conditions and see if it's binomial, and then we'll actually run through the problem and find the probability. So the first thing is we have to have a fixed number of trials. So every time you do this, you would have to randomly pick 8 people to be in your survey. So as long as that remains fixed, that satisfies condition 1. The second one is the probability of success or failure would have to remain the same every time you run a trial. So that's the 64%. There's a 64% chance that when you pick a person, that they'll say that they use their smartphones during meetings or classes. That's a fact about the population. So that remains fixed. The third condition, the second condition was that there have to be 2 outcomes, exactly 2 outcomes. So either someone uses their smartphones during meetings or classes or they don't. Okay, and then the third condition is the probability has to remain fixed every time you run a trial. So there's a 64% chance because you're pulling them from that population. And then the fourth condition is that the trials have to be independent of each other, which I think is a bit of an issue, but let's assume that they're independent. I do think that if I pull out my cell phone during a meeting or a class, that I might influence someone else to do that as well. So I don't know if it's completely independent, but let's say it is. Okay. It's pretty close to being independent. I think most people will pull them out independently of anyone else, but there could be like, someone pulls out a smartphone and they say, oh, okay, I'll pull out my smartphone. That would be a case where there's dependency. But let's assume it's independent, and therefore this would be a binomial situation. Okay, so then we want to know the probability that when you pick these 8 people at random from the population, we want to know the probability that exactly 5 of them say they use their smartphones during classes or meetings. And that's where we get into this formula down here at the bottom. So first of all, random variable in this case is the number of people or number of adults who use their smartphones during classes or meetings. I'm just going to say during class, okay, to make it easier. Out of the 8 that we sampled. So this is our random variable, okay? What could this number be? Well, it could be anything between 0 and 8, but it has to, well, not every number between 0 and 8. 0, 1, 2, 3, 4, 5, 6, 7, or 8. It can't be 1.5, right? Because we're talking about people here. So it's a discrete random variable, right? The numbers are jumping. And we just checked it. Not only is it discrete, it's actually binomial. And for that reason, we can calculate the probability using this formula here. And so we want to know the probability that this x turns out to be 5. Exactly 5, right? And when I do this, could be 0 out of 8, 1 of 8, 1 out of 8, 2 out of 8, 3 out of 8, 4 out of 8, 5 out of 8, 6 out of 8, 7 out of 8, or 8 out of 8. I wanted the probability that I get 5 people out of 8 who say they use their smartphones during classes or meetings. And so that's what this does here. So this calculates the probability that X will be a certain number. So X here is 5. So the probability that you get a 5 for X is, all right, I'm going to show you how it works in this formula. So N is the number of trials, right? So that's, in this case, 8 trials. And so it's going to be 8 factorial. Now, you may not have seen factorial. This is like an exclamation point. If you've never seen this before, it just means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's just a short way of writing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, whatever that number is. Okay, and you could do that on your calculator, right? Just multiply those together, and that's what this number is on top. It's called 8 factorial. On the bottom, you're going to divide by x factorial. Well, 5 factorial, right? Because x is 5 here. So that's just 5 times 4 times 3 times 2 times 1. And then n minus x factorial. So 8 minus 5 factorial, which is just a 3, right? 8 minus 5 is 3. So that's 3 times 2 times 1. Okay. And then we're going to multiply that by p raised to the x power, where p is the probability of success for one trial. Well, in our case, probability of someone saying that they use their smartphones during classes or meetings is 64%. Of course, I'm going to write that as a decimal, so 0.64 BRP. And by the way, Q is 1 minus P, and that's the probability of failure, and that's going to be 36% or 0.36. Okay, so P is 0.64, and we're going to raise that to the x power, which is 5. X is 5 here. And then we're going to multiply that by Q, which is 0.36. But we're going to raise it to the n minus x power. And n minus x is 8 minus 5. So that's going to be raised to the third power. Now, you could put all this into your calculator and figure out what the number is. It's kind of tedious to type all this into your calculator, but that's how the formula would work, okay? You just have to type all this in and see what you get. Now, I'm going to show you. Let me pull up the calculator. So you could type that all in the calculator, but instead of doing all that, I think it's just easier to use this. There's a distribution button on the calculator. Again, the 2 buttons we're going to use a lot in this course are the stat button, and then the other one is going to be this distribution button, which is the button above the VARS button. So you have to press this blue button first, and then the VARS button, and it's actually the distribution button. It says DISTR on top. And when you do that, you'll get this menu here, and it has a list of all the different distributions that we're going to look at throughout the course. So we'll touch on each of these at some point during the course. Notice the very top one says normal distribution, which is a bell-shaped distribution. That's going to be the most important one. We've already talked about bell-shaped a little bit, but we want to scroll down until we find the one that says binomial. You can see there's 2 of them. There's the binom PDF and there's the binom CDF. Now for this problem we're working on right now, we're going to need the binom PDF, and I'll show you the difference in a second. The PDF is when you're calculating the probability of exactly x equal to a certain number, like x is exactly 5. So PDF is x is exactly a specific number, like a 5. And then the first thing you got to put in here is the number of trials. So it's going to be 8, and then we're going to separate them by commas. So the number of trials is 8, and then comma, probability of success for each trial, and that's the 0.64. And then comma, what do you want X to be? And we're looking for X to be 5, exactly 5 successes. This is going to give us the probability that when we randomly pick 8 people from a population that where 64% of them use their smartphones during meetings or classes, that we'll get exactly 5 that do. And the answer is about 28%, 0.28. So there's a 28% chance that when we randomly pick 8 people from this population where 64% of them use their smartphones during meetings or classes, there is a 28% chance that we'll get exactly 5 of them that use their smartphones during classes or meetings. Okay, so that's how you work out that kind of problem. Now, again, it really comes from the formula that I showed you down here. And you could type this all into your calculator and you would get the same answer. It's just a little bit easier to use this binom PDF function. So before we go on, does anybody have any questions about that one? Everybody's okay with that one? Okay, so let's look at the next one then. I'm actually going to jump to number 6, I believe. Let me see. Yeah, so this one says it's kind of the same thing. This time, the population is 44% of them use their smartphones during classes or meetings. And we're going to randomly pick 13 from the population. And we're going to count up how many of them use their smartphones during classes or meetings. But this time, we want to know the probability that we get fewer than 4 of them that do so. Well, in order to calculate this, to figure this out, we need to actually calculate several probabilities. Fewer than 4 would be 0, right, out of 13, right? That's fewer than 4, or 1 out of 13, or 2 out of 13, or 3 out of 13. We need to find the probability of each of those, and then we need to add them up because any one of them would be fewer than 4. So we need to calculate the probability that we get 0 out of 13, and then the probability that we get 1 out of 13, and then 2 out of 13, and then 3 out of 13. And then we're going to add up those probabilities, and that will be the answer. That's the probability of getting fewer than 4 out of the 13 that say they use their smartphones during classes or meetings. So this is going to be, if you had to do this by hand, you would have to use this little formula down here several times. You'd have to plug 0 in for x and figure out what the probability is for 0, and you'd have to plug a 1 in for the x, and out that one, right? And then 2 for x, and then 3 for x, and then add up those probabilities. So that's going to be a bit of a pain to do. So, you could also do it on the calculator. So again, you would go to this binom. But you have 2 options. You could use the binom PDF. If you go through the binom PDF, you would go through and put in 0 for x, write down the probability. Put in 1 for x, write down the probability, right? And then 2 for x, write down the probability, and then 3 for x and write down the probability. And then you just have to add up those probabilities. So that would take a little bit of work, not quite as much as using the formula by hand. That's where the CDF function comes in. It saves you a little bit of time. CDF stands for cumulative. And what it's going to do is it's going to add up the probabilities up until the x that you put into it. So let's click on that one. So we're going to say binom CDF. And the first thing you do is you put in the number of trials. This time, I think it was 13. And then the probability of success was, I think, 44%. But let me pull it back up and make sure. Yep, 44%. So I'm going to put in 0.44. Then comma, now the x value that I put in is going to be the number I want to stop at. So it's going to start off at 0 and calculate the probability of x being 0. all the way up until the number that I plug in for x. And I think we wanted to stop at 3. Let me check it again. It was fewer than 4. So we want the probability of fewer than 4, so we're going to stop at 3. And number you stop at, the number you plug in, it's going to include in its calculation. So I'm going to plug in a 3. Now, what is this going to do? It's going to calculate the probability that x is 0, and then the probability that x is 1, and then the probability that x is 2, and then the probability that x is 3, and then it's going to stop at the number I plugged in, right? It's going to stop at 3. And then it's going to add up all those probabilities for us. And the answer is 0.1055, about 10 or 11% roughly. So to be clear, difference between the PDF and the CDF is when I plug 3 into the CDF, it's actually calculating the probability starting at 0 all the way up to 3, and it's adding up all those probabilities. It's an accumulation. Whereas when I do the PDF, when I plug the 5 in, it's only calculating the probability of exactly 5 out of 8. It's not adding them up, it's just calculating the probability that x is 5. Okay, so that's the difference between the PDF and the CDF function. Does that make sense? Okay, does anybody have any questions so far? Okay, so this, I think you can see this saves you a lot of time. I certainly wouldn't want to go through and do like I could calculate what I just did right here using the PDF function, but then I'd have to go through and do it for 0. And like I said, you would write it down, and then you'd put in a 1, write down the probability for 1, do it for 2, write down the probability for 2, and then do it for 3, write down the probability of 3, and then you would add up those probabilities, and it would add up to this number. So it does save you quite a bit of time using the CDF function. Okay, and then there's the one like number 5, and notice in number 5. Okay, so now the 43% of the population uses their smartphones during meetings or classes. We're randomly picking 5 of them from the population, and we want to know the probability that at least 3 of them use their smartphones during classes or meetings out of the 5 people that we picked. Well, at least 3 would be 3 out of 5, 4 out of 5, or maybe 5 out of 5. So we got to calculate the probability that x is either 3, 4, or 5, and then add up those probabilities. So it's an accumulation. But what's different about this problem is it's an accumulation starting at 3 and then going up to 5. So the calculator doesn't actually do it that way. It starts at 0 and ends at the number that you plug into it. So when I calculate this, if I go to Binom CDF, let me just show you. Let's say I go to Binom CDF. It's an accumulation, right? So I know I want to use CDF, not PDF. The number of trials here was 5. The probability of success for each trial was, let me check it again, 43% this time, so 0.43. Now, now I want to plug in, let's see, let's go back and look. I think it was at least 3. Okay, so a mistake would be to plug 3 in. Because if I plug 3 in, what is it going to do? It's going to calculate the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3, and then it's going to stop at 3. That's not what I want. I want the probability of 3 plus the probability of 4 plus the probability of 5 added up. So how are we going to do this? Because the calculator always starts at 0 and then goes up until the number you put in. Okay, so this is what we're going to do. We're going to plug in a 2. Now, why am I doing this? What's this going to give me? It's going to give me the probability of 0 plus the probability of 1 plus the probability of 2, and then it's going to stop, right? It's going to stop at 2. Now, that's not what I want, but that is the complement of what I want. So let me write this down so you can see it. So remember, the capital P stands for probability, right? So I'm just using this notation. The probability of 0 plus the probability of 1 plus the probability of 2 plus the probability to get 3 or 4 or 5 added up. And remember, there's 5 trials here. So this accounts for all the possibilities, right? It could be 0 out of 5, 1 out of 5, 2 out of 5, 3 out of 5, 4 out of 5, or 5 out of 5. So if I add up these probabilities, it should add up to 1, right? This accounts for all the possibilities. And now if I take these 3 probabilities, whatever they add up to, and I subtract them to the other side, whatever this number is, looks like this. Well, stuff that's left over here is the probability that I'm looking for. Because if you look back at the problem, remember it wanted probability of at least 3. So this is at least 3, right? 3 out of 5, 4 out of 5, or 5 out of 5. This is at least 3. So this is the probability of at least 3 right here. But I can't do this directly on the calculator. What I have to do is I have to say 1 minus binom CDF starting at 5 trials with a probability of 43% for each trial. Then I plugged in a 2. If I plug a 2 into here, it's going to calculate this probability, right? That's what binom CDF does. It starts off at 0 and it calculates the probability all the way up until this number here. So if I say 1 minus this number, I'll get the complement of this. The complement is this side, 3, 4, 5, and that's what I want. So on the calculator, that's what I'm going to do. So let's go back real quick. This gives me the probability of 0 plus 1 plus 2. What I want is complement of it, and if I want the complement, I just have to say 1 minus it. By the way, I'm going to put in the answer here. At the very bottom, there's an answer button, so I don't have to type it in, and it'll pick the previous answer. So that's this blue button right here. Well, hang on, I messed up. So let me try it again. 1 minus, oops, 1 minus the previous answer. So it's about 37%. So just to be clear, this turned out to be about 60, what was it? Let me look at it again. 63%, I'm rounding it off a little bit. This was about 0.63. And when I say 1 minus it, I get 0.37. And that gives me the probability of at least 3 out of 5. So you have to be careful on the calculator when you do this. If you plug, like I said, if you plug a 2 in, that's not going to give you the answer. It's going to give you the probability of 0 plus the probability of 1 plus the probability of 2. But if you take the complement of it, in other words, 1 minus it, then you'll get the probability that we're looking for here, which is at least 3 or more. Okay. Okay, so before we go on, does anybody have any questions about that one? Okay, just as a quick summary again, just to summarize this, if the problem says exactly 4, you can use the PDF and you just plug in 4 for X. If it says fewer than a number, like fewer than 3, then you can use the CDF function and you plug in the number that you want to stop at. You would start at 0. The calculator is going to start at 0, and then you plug in the number you want to stop at for X. So fewer than 3, you would want to stop at 2. So you could do binom CDF and just plug a 2 in for X here. And then if it's the upper side, so you're starting at some, not 0, but you're starting at some other number and you're going up from there, like this one says at least 3, then you're going to have to use 1 minus binom CDF of the complement, what you're looking for. So in this case, the complement would be 0, 1, or 2. So you'd stop at 2. You do binom CDF of 2 and take the complement of that, so 1 minus it, to get 3 or more. Okay. Okay, so then the last thing I want to look at is we can also calculate, you see the formulas for the mean and standard deviation that I mentioned. Let me pull those back up. If we have a binomial distribution, then we're able to find the mean of random variable, what happens on average, and how the data deviates from the mean. What's the standard deviation, in other words, right? This is a measurement of how the data varies from the center or the mean. That's called standard deviation. And you can see all you have to do is multiply the number of trials, the probability of success, and that'll tell you the average of the random variable, average outcome of the random variable. And then to get the standard deviation of the random variable, you would just have to say n times p times q and then take the square root of that number. Okay, so here's an example of this. This one says, based on a poll, 60% of adults believe in reincarnation. So this is kind of a fact about the population. Take this as a fact. 60% of adults from the population believe in reincarnation. And then we randomly pick 8 people from the population. Actually, this is the same problem we just did. This is not what I want. It actually turns out to be binomial. You know, when the probability is exactly 7, so you'd use the PDF function with a 7 for X. And so forth. Okay, this is not the problem I wanted. This is just like the ones we just did. Let's look at 9 instead. Sorry, let's look at the wrong one. So this one says, assume that hybridization experiments are conducted with peas having the property that for offspring there's a 75% chance or 0.57 probability that a pea has green pods. Assume that the offspring peas are randomly selected in groups of 12. Okay, so basically what's happening is you go through these hybridization experiments, and when you do this, there's a 75% chance that the pea that you generate will have a green pod in it. And so they do this for 12 different hybridization experiments. So they do this 12 times. And they want to know, on average, how many of the 12 will end up having green pods. Well, if you look at this, it's actually a binomial distribution. So the fixed number of trials is 12. There's 2 outcomes when you run a trial. You either have a green pod or you don't. A pea with a green pod or a pea without a green pod. So there's your 2 outcomes, right? Exactly 2 outcomes. The probability has to be fixed every time you run a trial, and that's the 75%. That's a fact about hybridization, I guess. 75% of the time, when you do a hybridization experiment, 75% of the time, apparently you get a green pod. So that remains fixed every time you run a trial. And then the last one is the trials have to be independent of each other, and I think that's probably true. I run a hybridization experiment over here that should not have, the outcome of it should not affect the outcome of another one, right? They have nothing to do with each other. So those should be independent. So yes, this is a binomial distribution. And what they want to know is what happens on average. So in this case, random variable x is the number of green pods out of 12 trials, right? Or p's with green pods out of 12 trials. And what we're trying to figure out is, okay, on average, how many out of these 12 will have green pods? And that's what this does for us. This tells us what happens on average for this random variable, what's going to be the average. And so the way you calculate it is you just take the number of trials and you multiply it by the probability of success. So there's 12 trials, and the probability of getting a green pod each time is 75%, 0.75 as a decimal. And when you multiply those together, you get 9. So on average, it should be about 9 out of 12, right? I mean, what you're doing is you're doing 12 at a time. So I do 12 at a time the first time, and maybe I get 8 of them with green pods. And the next time I do it again, maybe I get 10 out of 12 with green pods. And so what this tells us is if you keep doing this over and over again, the average is going to be 9 out of 12. That's what it averages to. Okay, that's what this means. So this is called the average of the random variable, or the mean of the random variable. What happens on average? But remember, x is the number of p's with the green pods, so out of 12. So every time we do 12, this number will be somewhere between 0 and 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11, 12. It's going to be one of those numbers, right? It's a discrete distribution. But on average, it's going to average up to 9. That's what this tells us. And then we can also calculate the standard deviation. Okay, so let's calculate that. So I'm just going to erase some of this to get it out of the way. So then you just have to take number of trials, which is 12, times the probability of success, which is 0.75, and then times the probability of failure. Well, remember, Q is the probability of failure. In this case, the probability of failure would be 1 minus the probability of success, which is 0.75. So it's going to be 0.25. Now, that's the probability that when you do a hybridization experiment, you would P without a green pod. It happens 25% of the time. That's considered failure here. And then you would take the square root of this number. Okay, so let me just calculate that quick. So 12 times 0.75 times 0.25. That gives you 2.25, but then you have to take the square root of it, which is this little blue. That's the square root that's above this button here, the little blue piece, square root. So I'm going to do second square root of the previous answer. I'm using that button there. And the square root of 2.25 is 1.5. Okay, so this is a measurement of how much the random variable varies from 9. By the way, if the standard deviation had been 0 here, that means there's no deviation from 9. That would mean that you're always going to get 9 out. I mean, you're averaging 9, but if the standard deviation is 0, then you're always getting 9. This tells us that, okay, there's some variation from 9. Okay, it's not always 9. Sometimes it's 8. Sometimes it's 10. It averages to 9, but there's some variation in fact that it's not always 9, right? It tells us how much it varies from 9. It varies from 9 a little bit. Okay. All right. Going back to the problem. And part B says, so that's part A, right? Part A was the mean is 9 and the standard deviation is 1.5. So then part B says, use the range rule of thumb to find the values separating results that are significantly low or significantly high. I call this usual values, which is unusual values. So the range rule of thumb basically says this. Anything within 2 standard deviations is considered a usual value. Within 2 standard deviations of the mean is considered a usual value. Anything outside of that is considered unusual, and that's called the range rule of thumb. So the maximum usual value is going to be the mean plus 2 standard deviations, and then the minimum usual value will be the mean minus 2 standard deviations. Okay, so for us, the mean was 9, right? And if I go out 2 standard deviations, now remember, standard deviation is 1.5. It's going to put me at 9 plus 3 is going to be 12. So anything above 12 is considered unusually high. Well, that's not possible here. Most you could get out of 12 trials is 12, right? You got 12 green pods, 12 peas with green pods out of 12. That would be right at the top of what we considered a usual value. Anything above 12 is considered unusual. So there's no way to be unusually high here, okay? Now, the minimum, though, the minimum usual value would be 9 minus 2 standard deviations. So that would put us at 9 minus 3 is 6. So anything less than 6 is considered unusually low. So if we got 5 out of 12 with green pods, then that would be considered unusually low. Okay. Now look, if this number had been 11, then 12 might have been considered unusually high. But actually, it's 12. So there's no way to get an unusually high number here. Okay. But you could get an unusually low number. Anything below 6 is unusually low. And that's what this range rule of thumb is kind of telling us. Okay. So if you go back to the problem, use the range rule of thumb to find the values that separate, what I call unusually low versus unusually high. So anything less than 6 is significantly low, and anything higher than 12 is significantly high, or unusual is what I would say, unusually high. Okay, so that's how you do part B. Then part C, you got 3. Let's say you ran the trial, right? You did 12 of these experiments. You ended up getting 3 peas with green pods. What would you say about that? You would say it's significantly low, right? It's unusually low. So the result is significantly low because 3 green pods is less than 6, right? Which is our boundary for being unusually low. Okay. Now, again, I want to emphasize this point. All these formulas that we're using, right? These formulas here, they're only valid for binomial distributions, okay? So you'd have to make sure that you satisfy those 4 conditions first, right? It has to be a binomial distribution before you can calculate the mean and standard deviation using these formulas. And that little probability formula that I wrote down earlier, right? You can only use this. I mean, this formula is only valid if you have a binomial distribution. So just keep that in mind. That's why those 4 conditions are important. You have to satisfy them before you can use both or any of these 3 formulas, okay? Okay, so, I'd planned on maybe getting to the next section in chapter 5, but it looks like we only have about 5 minutes left, so I think we'll just wait on that. But since we do have some time left over, does anybody want to go over anything? Do you have any questions about anything from this section? Okay. Well, I guess we'll leave it there then. Next time I'll go over 5.3, the last section in chapter 5, which is on the Poisson distribution, which is kind of a special case of the discrete distribution. Again, there's some conditions that we have to satisfy in order for it to be Poisson, and then we'll get some formulas that will be valid, and we can use them to calculate probabilities and means and standard deviations again for Poisson distributions. But we'll look at that on Monday, okay? All right, well, if nobody has any questions, I recorded this, so I'll send out the link to this later on today. And then don't forget about the first test being due on Monday, okay? All right, so have a good weekend, and I'll see you guys on Monday, okay?
Thank you.
No problem. Bye-bye.